In this talk, I'm going to discuss a control problem for martingales in a radially symmetric environment where we'll be able to find a closed form solution. This is joint work with Alex Cox and forms part of my PhD thesis, which I recently completed at the University of Bath. So the type of problem that we're going to consider is minimizing some expected cost over all continuous martingales that have unit quadratic variation. And what I mean by this quadratic variation condition is that at any time t, the quadratic variation of the martingale is just equal to t. Our martingales will live in a bounded domain in d-dimensional space. And we note that if d is equal to 1, then the only continuous martingale satisfying the unit quadratic variation condition is the one-dimensional Brownian motion. And so we're interested in the higher dimensional versions of this problem with d at least 2. Some motivation for this problem is coming from robust finance, where we might want to find a best case model under some minimal modeling assumptions, such as having a continuous martingale. And there are some connections here with martingale optimal transport that we'd be interested in exploring in future work. So let me define the problem more precisely. We take the control set to be the set of volatility matrices satisfying the condition that this norm here is equal to 1, and that gives us our unit quadratic variation. We're then interested in martingales X sigma that are strong solutions to an STE of this form, and the aim is to find the value function, which is minimizing over all such controls, where we have some running cost f on the interior of our domain and some boundary cost g. So we want to work in a radially symmetric environment so that we can get a closed form solution. And this means that the domain should be a d-dimensional ball of some radius r, and the running cost f should depend only on the radius, and the boundary cost g must be constant. Now we also need some extra technical conditions uh, in order for our proofs to work, and these we will actually be able to relax slightly and are not so important for what we're discussing today. Um, Now, the way that I defined the problem in terms of strong solutions to STEs is quite a strong formulation. However, there is a result from this paper of El-Kharoui and Tan that says that under our assumptions, there is a weak formulation that is equivalent to the formulation that I wrote down here, which is then much closer to really optimizing over all martingales that are continuous and have unit quadratic variation. So having defined the problem, let's talk about its solution. So for the optimal behavior, there are two martingales that we're going to consider. So first, suppose that our cost function f is monotonically increasing. Now, since we want to minimize the expected cost, uh, this means that it is favorable to spend as much time as possible close to the center of the domain. So supposing we start at some point here in the domain, we could draw a radius through the center of the domain and then move as a one-dimensional Brownian motion on this line until leaving the domain. And you can see a sample path on the right here of the radius of such a process. And this behavior can be achieved with this constant control where x is the starting point of the process and the radius point locally behaves like a Brownian motion. So this is the optimal behavior for a monotonically increasing cost function. On the other hand, if we have a cost function that is monotonically decreasing, then we'd like to spend as much time as possible close to the boundary of the domain. So you can see here on the left a sample path of some martingale x that achieves this, and the way that this martingale behaves is that at any point we're moving on a tangent to the current position, which has the effect of pushing the martingale out towards the boundary while maintaining the martingale property. You can see the sample path of the radius process on the right here looks as though it is deterministic and strictly increasing. So a control that exhibits this behavior is given here, where we choose some vector that is orthogonal to the position vector. And the radius process is indeed deterministic as the solution to this ODE, and in fact the radius is just equal to the square root of time. And you can see another example of this property, this particular martingale, being used in this recent paper of Larson and Wolf. So we've seen two different types of behavior, which we're going to call radial motion and tangential motion, that are optimal for monotonic cost functions. Now, our claim is that for a general radially symmetric cost function f that satisfies all of our assumptions, then an optimal strategy is actually to switch between these two behaviors, as you can see an example of in this simulation here. So to prove this claim, what we do is we construct a candidate for the value function and then verify that this is indeed correct. So since we're in a radially symmetric environment, we expect that the value function should only depend on the radius. And we also have this external boundary condition here. Now, in a region where the optimal behavior is radial motion and the radius process is behaving like a Brownian motion with this generator, we then expect this second order ODE to be solved. And in regions where tangential motion is optimal with the deterministic radius, then we would expect this first order ODE to be solved. And so the way that we'll construct a candidate for the value function is by solving these ODEs, having determined at which points we need to switch between the two behaviors. So we have a one-dimensional switching problem here that we're looking to solve. So given that we are trying to find the value function, which is the minimizer of our expected cost, and we fix down the right-hand endpoint at g, then this would be equivalent to maximizing this first derivative. And so the way that we are going to find the switching points is to compare the first derivatives of solutions to this second order ODE and solutions to this first order ODE. I'll demonstrate this now by means of a simple example. So suppose that our cost function is just the sine function, then since the sine function starts off increasing, we'd expect this radial motion to be optimal to begin with. I've then drawn here this point R1, which would be the first time that we switch to the tangential pushing out behavior, and this second switching point S1, which will be the first time that we switch back to the radial behavior. So how do we determine where these points R1 and S1 lie? So in this first region where we expect radial motion to be optimal, then we expect that the value function ought to solve this second order ODE with some boundary condition. And after switching at the point R1, we'd expect this first order ODE to be solved. Uh, Now we'd impose a continuous fit condition to solve this first order ODE. And then the way that we determine where the point R1 lies is by comparing the first derivatives, as we recall that we are aiming to maximize the first derivative. Then this point R1 here is chosen such that the first derivative of W1, shown in orange, becomes larger than the first derivative of U1, shown in blue, for the first time. Now, we're not requiring any smooth fit condition in order to solve this first order ODE. However, we note that because of the continuity of the cost function f, we actually do see the first derivatives matching at this point um, where they cross. And so we do get smooth fit as well as continuous fit. Now for the second switching point, S1, this is the first point at which we would switch back to radial motion. So in this region to the right of S1, we expect this second order ODE to be solved. And now, as well as a continuous fit condition, we need to impose a smooth fit condition in order to solve the second order ODE. So in order to then choose where uh, this switching point S1 lies, we actually choose it to be the first point at which the first derivative of U2 stays above the first derivative of W1 over some interval of positive length. And this is equivalent to considering the second derivatives, and the second derivative of U2, shown in blue here, should be above the second derivative of W1 for the first time at this point, S1. Now, continuing in this way, we can construct a whole sequence of switching points up until leaving the domain, and you can see the form of the switching points Ri and the switching points Si there for any cost function that satisfies our assumptions. And so, having found the switching points, we can solve the system of ODEs to construct a candidate value function that I'm calling capital V. And for some constants C that we can write down explicitly, uh, we find that the candidate takes this form here. And we're able to prove that this is indeed equal to the value function for this control problem. Let me give a quick idea of the proof of this result. So first of all, we would prove that the value function is the unique viscosity solution of this boundary value problem for a Hamilton-Jacobi-Bellman PDE here, just adapting some standard theory from stochastic control theory. And then we verify that our candidate value function V is also a viscosity solution of this problem and conclude by uniqueness that we have indeed found the value function. So to summarize, what we've done here is we've constructed a closed form for the value function in a radially symmetric environment and verified that this value function is indeed correct. We are also able to extend this result slightly to relax the assumptions that we had on the value function. And in particular, we can allow the cost function to become infinite at the origin. Um, and I've just sketched out here some growth conditions on the cost function f. And what we've shown is that in these regions shown in gray, the value function is still equal to the same candidate that we constructed previously, and we can classify when the value function becomes infinite. Noting that in this darker gray region here, although the cost function may become infinite, the value function itself remains finite. Now, in this highlighted region of growth here, we conjecture that there is actually a gap between the strong formulation of the problem that we've been considering in this talk and a weak formulation from the paper of El-Khoury and Tan that I mentioned earlier. And we've proved some results in this direction and will be interested to confirm this conjecture in future work. So I'll leave you with the two papers that I referenced in this talk, and thank you very much for your time.